Okay, thanks. It's a pleasure to be here. Both mix of new and old community in both substance and previous geographic locations. So it's, anyway, nice to be here. So I'm going to talk about property rights and the efficiency of bargaining. So it's a joint. There's a joint paper with Ilya Siegel. I guess we had one previous paper to this as well. I think the paper was distributed. I'm not sure, but anyway, I'll kind of give you a rough sense what's in it. So my aim is to, given the audience, I'm going to spend a few minutes just kind of giving you an introduction to the area, which I think is relevant for the other two speakers. Then I will tell you about kind of an overview of what our paper does, but then I'm going to just focus on the last part of the paper. And the reason I'm going to focus on the last part of the paper is that there's a result, or non-result is more accurate, a conjecture or a question that we have not been able to prove about something which is, whether the optimal solution is always close to a certain thing. And I'll tell you what that thing is, and I'll kind of at least show you some computation that kind of are suggestive. Okay. No, it doesn't. What do I have to do to make this go? What do I have to do?
Press forward.
Press forward, like that. Yeah. Oh, it worked. Okay, thank you. All right, third time's the charm. Okay, so in this paper, and I think generally in the other talks that you're going to see, there's a focus on what's the optimal allocation of property rights. And so what we mean by property rights is an initial allocation that serves as a default, a default position from which parties can then trade. Okay, so there have been various approaches to looking at property rights in economics, and it goes back to Aristotle, for example. But a more recent incarnation is due to Oliver Hart and Sandy Grossman and John Moore, who look at how property rights affect investments. That is, the idea is property rights are set as a default. Parties who are engaged in a trade relationship will, they're not able to contract ex ante, and then ex post, they may make investments, and the state of the world is then realized, and then they're going to bargain. And the initial property right position, in some sense, affects their bargaining strength, and therefore affects the returns that they can get from their investments. And so property rights then have an effect on efficiency due to investment effects. Okay, we're going to be interested in a different effect that property rights can have, and in particular that they can affect the outcome of bargaining and the efficiency of bargaining independent, like even in environments where there are no investments. Okay, now there's of course very famous result due to Coase, or the Coase quote-unquote theorem, that if parties can bargain, quotes were no good? Okay. I was going to put result, that quotes around result, and then I was like, no, I'll just put it around theorem. Okay. So if parties can bargain, property rights don't matter. That is, will reach efficiency don't matter for efficiency. They matter for distribution, but not efficiency. And parties will end up reaching an efficient agreement no matter what. Now, we've known for a long time that wouldn't be true, for example, in situations with asymmetric information. So there's, many of you are probably familiar with the Meyerson Satterthwaite result, a very famous result about bilateral bargaining between two parties that said that if there was under very general circumstances, if there's a buyer who owns a good, a seller who initially owns a good and a potential buyer, that there's no bargaining mechanism can result in efficiency. Efficiency for every realization of their values. Okay. Now, shortly thereafter, there was a result by Crampton, Gibbons, and Klemperer that was published that was put as a result about dissolving partnerships efficiently. But basically what they showed was that a sufficiently symmetric partnership would be able to be dissolved efficiently. So really what that was showing, put into this framework, this setting that we're thinking about now, another way to put it is, if you had intermediate property rights, for example, instead of the buyer and the not having any of the good and the seller having all of the good, if, for example, the default was 50-50 randomization as to who would get the good in the event that they failed to trade, you could reach efficiency. And that result has been extended. The previous paper that I mentioned with Ilya was a result, kind of a very general result showing, conditions under which a particular randomized property right would work in realizing efficiency. Okay. So what we're interested in this paper, though, is more generally in looking at settings where you can't achieve efficiency, what is the optimal property right to have? Okay, in settings where the inefficiency is due to asymmetric information bargaining. Okay, all right. Now, this question also has a life outside of economics in the legal literature.
So, sorry, optimal in terms of
I'm gonna say in a couple minutes. But welfare, yes, but I still have to tell you more. Okay. So it has a life as well in the legal literature. Luckily, we're right by Harvard Law School. And so where this comes in is discussions of what are optimal legal regimes. So there's a distinction in the law between what are called property rules and what are called liability rules. Property rules would be, for example, if someone is polluting, the law says that firm is not allowed to pollute. We will stop that firm from polluting. Okay, or there's a maximal amount of pollution they can do, period. We will prevent them from polluting more. A liability rule instead is a situation where the firm can pollute, but it's going to have to pay damages to the victim. Okay, so you can sort of think of that liability rule like it's a different sort of property right. In particular, it's an option. It's an option to own the ability to pollute. So the damage is like the strike price in an option. You can choose whether to pay it or not. If you pay it, you basically have bought the right to pollute. Okay? So that more generally kind of raises this question of, okay, we can not only have simple property rights, okay, like property rules, but we can have more complicated notions of property rights, and you can think of that option to own like a particular kind of mechanism that gets played in the event of default. Okay? So in this legal literature, Calabresi and Melamed suggested that this old theme that property rules are good for Coasian bargaining. It's never quite clear exactly why. But liability rules are more efficient when bargaining is not feasible. Okay, and their idea was quite simple, which is if you can't bargain with each other, then at least a liability rule makes the final outcome responsive to values. So the firm that has an option to pollute will choose to pollute if it has a high value from pollution. And that can improve efficiency. Okay? And in general, in that static setting, a liability rule is going to be better than a property rule. Okay?
Tie these two together. So you started with an example beforehand with an item that the buyer and seller were negotiating over. And now we're talking about polluting or not, and then not connecting them.
Okay, pollution, it's a bad, but for the firm, it's a good. The ability to pollute is like an input. Okay? So in that sense, they're bargaining over a good. Okay? So the literature then, more recently has had a number of papers that have kind of said, well, wait a minute, bargaining could happen after a liability rule too, and maybe liability rules can be better than property rules even when bargaining is possible. And in fact, if you think about the Coase theorem would say at the extreme where you have perfect bargaining, it doesn't matter which of these things you do. Right? So at that extreme of perfect bargaining, they're tied. And so we're going to have kind of a horse race between these two, and maybe with imperfect bargaining, we know that with no bargaining, the liability rule is better, but with imperfect bargaining, maybe we're going to be better off with liability rules as well. Okay? All right. So that's kind of the other connection of what I'm doing. So what do we do in the paper? So we do three things. One is we start off with a result characterizing conditions under which you can't get efficiency, under which efficiency is impossible. So it's a, you can apply it, it are a sufficient set of conditions under which efficiency is impossible. The Meyerson Satterthwaite result, for example, is a special case of those conditions, as are a number of other results in the literature. But the main point of that is to just establish a set of environments in which efficiency is impossible. And those are the environments in which we're going to be asking, what's the effect of property rights? OK, the next thing we do, coming to Jason's question, is we start asking, what are the optimal property rights? So if you reallocate property rights, when efficiency can't be achieved, how do you want to allocate property rights? And we're going to take the view that we're interested in welfare, in some sense in welfare, but there are two ways that you can do this. One is to say, so if you are familiar with the Meyerson Satterthwaite result, one way of viewing the result is that you can't get efficiency because there isn't enough surplus to subsidize trade. That if only you had more money to inject, like a subsidy to trade, you could get efficiency. Okay? So one approach you could take is to say, well, we want to achieve first best. We want to achieve efficiency, but let's look at the property rights that minimize how much subsidy is required to do that. Okay? So that's the first half of the paper. It turns out like getting very general results in that environment, was that mine? Let's answer the phone now. Text her back and just tell her I can't talk right now. No, it's okay. OK, so all right. So one thing you could say is, well, let's see which property rights would minimize the subsidy we need in order to achieve the first best. Okay? And it turns out you can get some very general results about that, and which we do. Probably the most striking result, which is of relevance for what I'm going to talk about going forward, is that if there are two parties, the optimal simple property rights and the optimal liability rule are both identical to if you can't trade at all. So the simple, static, extreme case that, let's say, Calabrese and Mulliman were interested in, and that some others like Steve Chevelle and Louis Kaplan looked at, where there isn't any trade at all, we're just looking at what's the optimal property rule, given that the agents are just, say the polluting firm's just going to decide whether to pollute, and there's not going to be any bargaining. If you look at what the optimal property right is for that, it's also the optimal property right that minimizes the subsidy. Okay, so all right. Now, okay, and let me just say one thing. So what is, I should lead into later. So what is, in that setting, the optimal liability rule, for example? It's that what you want to do is make the damage equal to the victim's expected harm. Okay, very intuitive, because what you want to do is get the party who may damage, who may pollute, to internalize the cost of pollution. And if you make the damage equal to the expected harm, they'll make the efficient. That's the best you can do. Okay. I'm not saying it's first best in general, but it's the best you can do in terms of a liability rule. So that's also the best liability rule to minimize the subsidy. Okay.
Can I ask a question on your second bullet?
Yeah.
So,
that's what I'm about to come to.
Oh, great. Maybe I won't ask the question.
Okay, let's find out. So what I'm going to talk about today is instead a different criteria, which I think in some sense maybe is, I don't know whether to call it more natural or to me of greater interest, which is to say, in many settings you don't have anyone who's going to subsidize trade. And so let's find the property rights that are most efficient given that, that maximize expected surplus, but subject to budget balance. Okay, so that's what we do in the last part of the paper. And the thing is, in that last part of the paper, it's much less, you are much less able to get general results. So you'll see, I'm going to be working actually back in the Meyerson Satterthwaite environment when I get to that. Okay? Do that.
So in the Meyerson Satterthwaite environment, we start with a property right, which is the seller has the property right and the buyer can potentially buy it from the seller.
Right.
And in your second bullet, you say you want to look at optimizing property rights.
Yeah.
So changing that setting from the seller has all of it.
Right, so
when I can sell it, you can do 50-50, which is what you were example before, and then you get efficiency.
50-50 will get efficiency. So what I'm actually going to be spending my time on is not looking at that. So if you could randomize, we know you can get efficiency. Suppose you can't randomize. And in that case, I can't do the 50-50, but let's go look at the optimal liability rule. So that's what I'm going to be asking about. Okay? Now, if you think about that liability rule, the two extremes of it are property rules. Like if you set the price equal to infinity, the guy will never pollute. It's like he doesn't own the right to pollution. And if you set the price to 0, it's like he owns the right to pollution to start with. So what we're really going to end up asking is, are those extremes optimal, or is there something in the middle that's better, and what is it? Okay? All right, so the general model, which is more general than what I'm going to be talking about, is very familiar, I think, except for just the property rights. An agent's a non-monetary decision X, monetary transfers T. Each agent privately observes his type, theta I. The payoff of agent I is VI of X, VI plus TI, where of the decision and your type. So it's private values. Types are independent random variables. Okay? So we have independent private values. A mechanism specifies, an allocation rule and a transfer rule, okay, or a direct mechanism does. An efficient decision rule is one that would maximize the sum of values. All right, property rights mechanisms. So in general, like I talked about, simple property rights like property rules or liability rules, which are like options to own. You can imagine more complicated mechanisms as your property rights. Okay, so in general, you might imagine property rights mechanisms that get played in the event of default. A property rights mechanism will induce some status quo outcome when agent I opts out. So, and let's define what agent I, that outcome as X hat I and Ti hat, where Xi hat is the decision, and Ti hat actually, the full outcome describes what everybody else gets, what all the other transfers are, but what will be relevant for me is just what Mr. I gets. Okay? And that's a function of the types. So for example, in a liability rule, the outcome depends on the polluter's type. It depends on his value of pollution, what he'll end up doing in that property rights mechanism, where he gets, basically, think of that, the liability rule as you make an announcement, yes or no, or my type is above a certain level or below, okay, my value for polluting. And so it's a particular mechanism where you're making an announcement. It's just a mechanism where only one side makes an announcement. The victim doesn't make an announcement in that mechanism. Only the firm does. Okay. And so the agent's status quo payoff is VI hat. We can write as some function of his type and the other's agent's type in general. And it's just his value of the default outcome. Okay? Under the property right regime. And for example, we can say, a particular property rights which induces some status quo permits efficient bargaining if there, and now we get into what I mean by, how I'm doing the mechanism design. If there's a budget balanced, incentive compatible, and individually rational mechanism that implements an efficient decision rule. Yeah.
Can you clarify why the status quo outcome still depends upon my type if I'm opting out and not reporting my type?
Suppose you're the firm and we're bargaining, and I say I walk away from the table, but I have the option to pollute. So what I do when I walk away from the table under that option depends on what my value of pollution is. Okay. All right. So let me just say that I think there's an interesting, so this is kind of the standard definition that comes up in the literature. It's what,
Hold on. I walked away.
Yeah.
When everyone transfers from the vector theta.
If everybody.
So how do we go to everyone else? So is this theta, for people not I, is the transfer depending on theta, or theta j or theta hat j or some reported theta j, or how I walked away and no one else did, right?
Yeah.
And we have this thing, ti hat of theta, which is the vector.
Right. So under the, I guess the property rights mechanism is specifying some game that everybody plays. I think, you know, it is the interpretation is much less of a question in the case of 2, which we'll be talking about. I agree that, you know, I think exactly how you treat the other guys when when one person walks away and what they're going to continue to do.
And
Yeah.
how is whoever going to learn their types, put their types into my transfer? My transfer, I'm player I walked away. My transfer depends on the actual types of everyone else.
No.
Well,
Oh, I'm sorry. So it depends on the actual type, but in equilibrium, in other words. So in other words, so strictly speaking, the way this is working, you know, and we can say whether it's realistic or not. I think there's more of a. I think with 2, it's not really an issue. Is if we have a breakdown, someone opts out of the mechanism, then we go to some room and we play a game, which is specified and depends on who walked out. You know, basically who we can tell who opted out. Now, I guess you could put, you know, there could be restrictions in some cases that you don't know who walked out, in which case it would be the same game regardless. Okay, we go and we play that game, and the outcome of that game depends on types. Okay, that's strictly what we're doing.
well, we deliver just pick one and
Yeah, I think they're, you know, they're like.
Okay.
Okay. All right, so these are all pretty standard definitions, except just to be clear about individual rationality. So budget balance says the sum of the transfers is 0 in every state. Bayesian incentive compatibility is what we mean by IC, by incentive compatibility. And then we're looking at individual rationality means interim individual rationality, where the status quo is this outcome that we've defined. So basically each type theta I, taking the expectation over what the other types are, has to be at least as well off in the mechanism as he would be or she would be opting out and getting this default payoff, which depends on, as we were just saying, I's type, and also we're looking at an expectation over the other types. Okay? All right. Actually, there was one. Let me just go back for one. Oh, let me just say, I think a second question. So one question of interpretation is what you said. I think I just flag. A second question of interpretation is what do we mean by a bargaining mechanism? So this literature, Meyerson Satterthwaite looked at these conditions because they're necessary in any bargaining mechanism. When you get to Crampton, Gibbons, Klemperer, and all of the literature that follows, they also look at this. But you might ask, okay, are there more stringent conditions in more restrictive conditions that are true in, quote, bargaining mechanisms? And literature hasn't, for example, maybe it's ex post IR or something like that. So it's not quite clear. There's a question about that. Okay, so now let's come to the part that I said I would talk about. So we want to look at second best optimal property rights in the Meyerson Satterthwaite setting. So we have a quote buyer seller setting. Really, what I mean is two agents. There's one unit of a good. They each have values for that for consumption of that good. I'll normalize to make those values on 0, 1 in the examples I look at. And so, just as I said, second best optimal mechanism is going to maximize expected surplus subject to budget balance, IC, and IR. Okay. Now, what's tough about solving, what's hard about solving these problems is that when you're doing this mechanism design, the optimal mechanism depends a lot on which types it is who are least willing to participate in the mechanism. Okay, that in the literature gets called critical types. Okay. In Meyerson Satterthwaite, it's trivial because the critical types for the seller, the guy who's least willing to participate is the highest value of 1. For the buyer, it's a value of 0. So you know from the beginning in Meyerson Satterthwaite what the critical types are. Here you don't. Okay? All right. All right. So simple property rights we kind of talked about. What you can show is that efficiency improves as you move towards the interior, randomizing. And eventually you can sustain the first best. So what we're going to do is say, let's suppose we can't randomize, what's the best liability rule? Okay, so I'm going to just say, we're going to pick someone to be what we call the active agent, the one who chooses under the liability rule. We'll just say it's agent 1, okay, without loss of generality. Okay, so let me talk about critical types. All right, so what you can show is that the critical type for the active guy is either type 0 or type 1, or both are binding. And so this is the little pic, just to show you why that is. Sorry, it's the only white board I have available. But if you think about, suppose there's a strike price, a price P that the guy has to pay for pollution. If his value is below it, his payoff is 0 in the default under the property rights mechanism. And then if his value is above, if theta, let's say theta 1 is above P, his value goes up with a slope of 1. Okay? Now, a standard result in mechanism design is that in the mechanism, the derivative of utility, of expected utility for the agent who is, for an agent, is equal to the probability he's getting the good. Now, that's always between 0 and 1. So we know that if I draw in the utility curve as a function of theta in the mechanism, its slope is always it's always non-negative and never steeper than 1. So as a result, either you have to be binding here, or you have to be binding here, or you can be binding in both. Okay? So those are the critical types for the guy who has the option. For the passive agent, the guy who's the victim, the critical type in the mechanism is the type who has the same probability of getting the good in the mechanism as under the default. So in the default, the firm faces a price P and is going to exercise with some probability. In particular, if F1 is the distribution of theta 1, it'll be the probability of pollution is going to be 1 minus F1 of P. It's the probability that the active player, the firm, has a value above P. Okay? The critical type for agent 2 is the guy in any mechanism is a guy who has exactly that same probability of getting the good. And the reason is that no.
You said F, right?
No. So F is in the default. Okay, what I'm saying is take any mechanism. The critical guy of the victim in that mechanism has to be a guy who has the same probability of trade in the mechanism as under the liability rule. Okay? And the reason is, take that guy, when he thinks I'm either in the mechanism or I'm out, I get the good with the same probability either way. So whether I want to be in or out is just a function of the expected transfer. If the expected transfer is bigger in the mechanism, I'll be in. If it's bigger out of the mechanism, I'll be out. Okay, now think about any other agent in the mechanism lying and saying he's that guy's type. Well, he gets the good with the same probability then in the mechanism as he would if he opted out. Okay, because he's lying and saying he's the guy who gets the, suppose it's out, suppose this probability of, theta 1 is the active guy, theta 2 is the guy who's the victim. So the likelihood that Mr. 2, the victim, or gets the good means no pollution. Let's suppose it's a quarter. Okay? That the probability of that theta 1 is below P is 1/4.
Mike?
Yeah.
You're looking at liability rules now. So this tells us how things work if no one opts out. Are you committed to what happens if someone does opt out, what this game is?
Yeah, it's a liability rule.
So what's the game as people opt out?
Sorry. So what I'm saying is the property rule is the liability rule. It's the probability that Mr. 2 gets it as a quarter.
And this mechanism on top of it.
And I have a mechanism that we're playing, and the question is, who is the guy least willing to participate in the mechanism?
I got twisted.
Okay. So just to finish the thought, so the guy who's, is the guy who has the same probability. Because if that guy's willing to be in, everyone's willing to be in, because they can all lie in the mechanism, say they're that guy, get the same probability of trade that they would outside of the mechanism under the liability rule. And we already said if our critical guy is willing to be in, it's because the transfer is bigger, so everybody else would be better off in too. Okay? So those are the critical types. Okay, I'm over. This is, I'm
You have-
sorry.
Take 4 more minutes.
Okay, so what do? We solve this problem. So we find a way to solve this problem. It's a little involved. Basically, we look at a relaxed problem where what you do is you pick a critical type theta 2 hat, okay, for the victim, an allocation rule, and the interim utilities, so everything is the same as normal, except that you're also picking this critical type. And you do it subject to budget balance, first order incentive compatibility. So we're relaxing, as everyone always does, we're relaxing incentive compatibility initially to just be the first order. You have to satisfy the first order conditions. Agent 1's participation constraints that both type 0 and type 1 want to participate, because those are the critical types for Agent 1, the guy who's choosing under the liability rule. And then 2 conditions for Agent 2. The first condition I've written here, which basically says if you're type theta 2 hat, so what this is saying, do you have a higher probability of getting the good in or out of the mechanism? Okay. So what it's saying is, if you have a type above theta 2 hat, you have to have a higher probability of getting the good than under the opt-out, under the liability rule. And if you're a lower type, you have to have a lower probability. And that's a necessary condition because in mechanisms, we have single crossing basically, or supermodularity, or increasing differences. So that's going to a condition that has to hold in any equilibrium, but it's weaker. Anyway, so it's a necessary condition. The other thing is we're only going to then impose the IR constraint for Agent 2. Okay? So it's a relaxed problem, but we end up showing the solution to that, finding the solution to that, and then showing that it's the general solution. Okay? What it looks like, I'll just kind of show you a picture. Let me just go to Meyerson. This is a general characterization. Let me go to Meyerson Satterthwaite. So those of you who are familiar with Meyerson Satterthwaite, you remember there's a gap, there's an inefficiency. So here, this is a picture of what the solution is if the price in the liability rule is above 5/8, a high price. So under high price, you should be kind of thinking, okay, the active guy is kind of like a buyer. Like he doesn't, a high price, price of 1, he would be just like a buyer in Meyerson Satterthwaite. So what ends up happening is you get, for values, below P, you get this Meyerson Satterthwaite gap. Above P, actually you have efficiency. Okay? And then it's the flip if P is below 3/8. And then in between, so this is a situation where actually the IR constraint that binds is for the active guy is type 0. It's just like a buyer in Meyerson Satterthwaite. It's the lowest value guy who has his IR binding. If P was below 3/8, you'd be close to the case of the Meyerson Satterthwaite seller, and it would be type 1 that was binding. And then in between, actually both IR constraints for the active guy bind, and the solution looks like this. So you sort of have this interval where the probability of trade is, where the cutoff for trade is not changing. So the shaded area is where Mr. 1 gets it. The area down here is where Mr. 2 gets the good in the end out of the mechanism. Okay. Let me just show you. So one kind of interesting thing, let me ignore everything else. Just this black line is showing you surplus as a function of P. So one interesting thing is, unlike the case of simple property rights, liability rules that are close to a simple property right are worse than the simple property right. Moving to the interior in terms of the price does not improve things initially. It makes them worse for efficiency. So this is loss, not efficiency. Okay, sorry. This is loss. So this is an example where both guys are uniform. Okay, which is the picture I was showing you a minute ago. So 0.5 turns out to be the optimal P, but it's not monotone. Moving to
Yunku, I want to let Mike state his conjecture, and then I want to get the question.
Okay. All right. So, okay. So here's the thing. In this picture where it's symmetric, both guys have a uniform distribution, Optimal P is 0.5. That's also the optimal P in the event we didn't have bargaining at all. Without bargaining, remember what you want to do is set the price equal to the expected value of the victim. Here, Mr. 2. And with a uniform distribution, his expected value is a half. Okay? So the question is it just like with the expected subsidy, is it true that it's always equal to the expected value of the victim? Okay, the answer to that is no. Okay, so let's, oh, sorry. Let me just show you a little, how do I get this thing to come back alive? Oh. Actually, the computer is blank.
Yeah,
So.
just control L again. You're not going to get it to come alive again, like with a lot of effort. So can you just press that, or you need to show something else in the computer?
I was going to show another picture. All right, let's leave it aside. I don't need to show you the picture. All right, so here's what happens. So it turns out in all the, so we then looked kind of computationally at different examples that weren't uniform and that weren't symmetric. It turns out that in all of these cases that we've solved, in most of the cases we've solved, the optimal P is not the same as the expected value of the victim, okay? But it's very close. I mean, very close. But so close that for a long time, we were worried it was just computation, that we were like just not getting things accurately enough to tell that it was the same, okay? But we've now have examples where we've done it very, very finely, and what you can see is it's really, really close. So if the optimal value of the victim is 0.6, like what I was going to show you in this other slide, it turns out the optimal P in the liability rule might be 0.62, okay? And we've done this down to thousandths. And so, number one, it's very, very close in P. And of course, you know that if it's very close in P, the expected surplus in that outcome, in the optimal thing, is very close to the expected surplus you would get if you did the static thing, just by the envelope theorem, right? So the question is, what we haven't been able to show, is very tantalizing because you think, okay, maybe there's some result that, that bounds how inefficient the static thing can be. Okay, the optimal static, setting the P equal to the victim's expected harm, that bounds how bad that can be, and it's always very close to the optimum. Okay, but we haven't been able to show it. Okay, and we're not quite sure how to show it.
I just want to add on to Mike's little piece of intellectual history that I think highlights what an important question this is, which is that Coase stated his theorem as a reaction against an older Pigouvian tradition, which said that you should have these expected liability rules effectively. And he said that's not necessary, that's not even good, just give people property rights and they'll sort of figure it out. Or at least that's the bad interpretation of what Coase said. So that Coase wouldn't actually express it that way, but Stigler sort of interpreted it that way. And so in some sense, what Mike's result is suggesting is that actually the old Pigouvian tradition was more right.
The result.
Yeah, exactly. So,
yeah. So anyway, so that I thought would be perhaps the most interesting, thing in terms of the connection, because to the extent you guys have ways that you think about bounds on outcomes of mechanisms, that's what's going on here. But we're not sure. I mean, at least as I said, all the examples we've calculated have this feature. So
Yunku, you had a question?
Yes, I was having just a clarifying question. So actually, before that, I found what's happening around the extreme also to be really fascinating.
Yeah.
Because what has been also very challenging among many people is to rationalize why extreme property might be justifiable. And there are many sort of informal theories that people like Kapilo, Chabert put forth. Wasn't very convincing. But here you get not exactly global optimum, but
Right.
something that is local optimum.
Yes.
That's quite interesting. So, but just by looking at the picture, here is the clarifying part. Looking at the picture before, when you have this, even for extreme P, it looks as if that you are adding more region for efficiency, right? So if you're starting from Meyerson Satterthwaite wedge, right?
Yeah.
By having liability rule, you are adding some region of efficiency. Of course, it doesn't say anything about what happened to the wedge, the size of the wedge. So what's going on might be the starting from the extreme property rule.
Yeah.
When you are lowering P or raising P from 0 slightly, you are adding this region of efficiency, but you are expanding the wedge more.
So this I can explain.
Yeah.
You know, this I understand. So the problem there is that when you move a little bit away from an extreme property right, you're actually making everybody better off in the default, essentially. So basically, think about we start with a price equal to 1. All right? The active guy is definitely, for whatever his type is, he's better off with a slightly lower price because it's better to face a lower price. Okay? Now think about the passive guy. The passive guy, initially there's no, basically in the default, there's no trade. Right? The option never gets exercised, but the option price is starting at 1, which is bigger than essentially every type of the passive guy's value. So the passive guy actually would like to trade. Every type of the passive guy would like to trade at 1. Okay? And so when you lower P a little bit, essentially almost everybody of the passive guy is better off. And then the trick of the result is actually to show that you can deal with the little set of guys that have just been, you know, who aren't below the new price. But
making them better off is actually a bad
and we can
thing.
making them better off in the default is a bad thing for
Right.
getting
Yeah.
the mechanism
Yeah.
to surplus.
Yeah.
So that's why that happens. I understand that. It's the other thing that I was describing about like P close, always seeming very, very, optimal P being very, very close to the victim's expected harm. I don't understand. Like I don't understand it. I don't know how to show
Why
what.
would you expect it to be close outside of normal?
Well, in the static world, I gave the reason. In this bargaining, well, if I had a strong intuition for why I would expect it to be close, I would have some clue onto why. Like I've been very surprised that it seems to always be so close. It's so.
Try to like handcraft through prayers to make it not be close.
So we've played around compute. I mean, the thing is we've got to compute these things. And so we've looked at several classes of density functions for the two agents. And whenever we do, it's very close. Now, I'm not ruling out that there isn't some other density function that we haven't tried that would turn out like not to be close. If I knew the answer to Nicole's question, I'd have some idea of like, well, what density function might I look for that would screw things up? Glenn had a suggestion. We tried that at one point. But so I don't know. So one possibility is there are other densities that it's not true for. The other possibility is there's actually some bound result there that we don't know how to show. So
The mechanisms we're talking about, though, are different.
different.
You're comparing someone just having an option FP to pollute versus this other more complicated.
Well, to be clear, what I'm doing is I'm saying we are going to set the option to pollute as the default, okay, with that damage level P. And we're going to build any mechanism we want on top of it, subject to the usual conditions that nobody wants to, that's IC, no one wants to opt out, into the liability rule. That no one wants to opt out of this bargaining mechanism and have the result be that the firm just decides whether to exercise the option. And then what we're comparing is what price for that option, for that liability rule, results in the greatest possible surplus in the mechanism, the bargaining mechanism we construct on top of it. And what I'm saying to you is the one that's optimal is always, in all the examples we've looked at, extremely close, but not the same as the optimal price you would get if you said, forget about bargaining, what's the best option price if we just have the firm decide whether to pollute or not, which is.
Yeah, so my question is, if we were to look at the outcomes that arise from these two mechanisms, one, the optimal with no bargaining afterwards, and the other, the optimal when you can have bargaining afterwards,
Yep.
where you say these prices are very similar, but one of them has bargaining afterwards. And I'm wondering if the second stage of bargaining afterwards really changes the outcome, or is it actually almost the same outcome in the first place?
Yeah, well, you can see that because I showed you what it looks like. So like that is the outcome of the optimal mechanism. So take the example that was P equal both guys uniform, okay? So with both guys uniform, I showed you P equals a half was optimal, which is in this case. So this is the decision rule. The decision rule has Mr. One, the active guy gets the good up here. The passive guy gets the good down here. The victim gets the good for those values. What happens in the static world is it's just a line. This would instead be a line all the way across.
I see.
At
So
P.
you're swapping that triangle for that triangle.
Exactly.
Exactly.
Now,
I think we have to move on to Yunku for now.
We can talk
but,
later.
We'll talk more later, and
Yeah.
I'm glad people are so interested.
Great. To go to bed.